Hello, can you hear me? So I'm going to talk about a task called Semantic Dependency Parsing and some multitask settings to try to improve some results. So I'll present the task very briefly and then the datasets that I've been using. I'll present very quickly the main current approaches and then with a focus on how the interdependence between the arcs in the target representation is handled. And then I'll present my proposal. So the task is that you have, you have an input sentence and you want to, the target representation is a graph of bilexical dependencies whose exact linguistic status varies across datasets. So here, for instance, she is represented as the first semantic argument of two different predicates, here coordinated predicates. So the idea is you go beyond plain syntax and up to semantic graphs or some representation in between syntax and semantics. So I've been using datasets in English and in French. So the English graphs derive from shared tasks that occurred in 2014 and 15. These are conversions of rich annotations on the Pentry Bank sentences. So there are three annotation schemes with slight differences. I show you some example. Maybe it's too small. So in both representation here, you have this idea of numbering the semantic arguments, but it's more, it's going up to various levels of abstraction over the syntactic representation. So for instance, here you can see that the argument of apply in both cases is recovered as technique. A similar technique is almost impossible to apply. But for the adjective impossible, here you see that in this graph you have correctly only one semantic argument, whereas in this case there are still two arguments deriving from the syntactic representation. So in this case, it's rather wrong. So it's just to tell you that these representations have been obtained through various conversions, and there are problems in them in these graphs. But this is the target. For French, we've been working with people in Nancy, Bruno Guillaume and Guy Perrier, and people in Paris, Corentin Ribert and Jamé Seda, to produce deep syntactic graphs. So here the labels are still syntactic, but we consider a graph. So for instance, député here has 4 incoming args. It's considered as an argument of 4 different predicates. And the labels are kept syntactic because in the absence of a semantic lexicon, the numbering of semantic arguments is not very informative. And there is in these graphs, we have tried to neutralize some syntactic alternations. So from frequency point of view, the phenomena that are massive are control and raising, passive alternation, and VP coordination. So as far as the techniques to produce such graphs are concerned, so the current approaches for semantic dependency parsing are adaptation of parsing algorithm defined to output trees, dependency trees, and you relax the constraint of having only one head per word, and you get a graph. The main improvements currently stem from the encoding of the tokens, so with contextual representations, transformer-based pre-trained models, etc., and recurrent encoding. So there's not much work on the algorithms, parsing algorithms themselves currently. And we find the rather old approaches such as transition-based parsing. So you have originally it was proposed for trees, and you have recent instantiations that are both neural and that output graphs. And the main characteristic is that it's a sequential processing over the sentence. So the good point is that when you process a word, this is an oversimplification, but when you your current word to process is, say, partir here, in Kim veut partir. You have access to the previously predicted arcs, and you can use them as in the encoding of the token to process. The downside of such an architecture is that you have error propagation throughout the processing of the sentence. Another typical approach is the so-called graph-based parsing, originally proposed to output trees. And the main idea is that you are going to compute a score of the overall graph or the overall tree, and you compute that as a sum of scores of some subparts of the graph. And if you do the so-called order 2 graph-based parsing, then you will sum scores of pairs of arcs. And you have recent instantiations of this architecture. So the good side is that because you process pairs of arcs, you are able to capture some form of interdependence with arcs. But the downside is that obviously the inference is complex. So that's why people often stick to the so-called order one parsing, where you only consider arcs, single arcs. In particular, you have a very famous parser that is the Biaffine parser, where the arcs are scored individually and independently from each other. So it's simple and highly parallelizable because you can compute the scores of every candidate arc at once. But the downside is that you score the arcs independently from each other. And it works surprisingly well given that drawback. So the work I'm presenting today is a reflection on how to keeping this architecture, how you can inject some form of interdependence between arcs. So the context was that we could measure performance of such an architecture on the French syntactic graphs that I showed you before. So, respect to the previous state of the art, which was a non-neural architecture, so we have a great improvement, obviously, because of the neural architecture and the pre-trained language model. So this is typical of current NLP. But as usual with machine learning techniques, it works very well overall, but still you have very gross errors if you do error analysis. So for instance, you have sometimes, the parser sometimes predicts some totally incompatible arcs. And for instance, so here, dans l'hexagone pour la première fois, here pour la première fois, is encoded in the gold graph. It's encoded as a multi-word expression. Using a flat representation, the first component of the expression is the other components are attached to the first component. Yes. And so it's totally impossible for this component to have another incoming arc, which actually is predicted. So such inconsistencies are a bit strange, and they stem from the fact that the arcs are predicted independently from each other. So I'll go a little bit quicker, I think. So the proposal is to use the framework of multitask learning. So we have the main tasks that are predict the arcs between the words and predict their labels. And then we're going to add some auxiliary tasks. So for each token of a sentence, we're going to try to predict its number of heads, its number of dependents. So here for député, it would be three heads and one dependent. And we are going also to predict the full set, multi-set of labels of the incoming arcs. So here, for the 3 incoming arcs to député, you would have such a label. So the underlying intuition is that with multitask learning, you train your model with some parameters that are shared. In our case, we share the recurrent representation, the BLSTM representation. So one example of hypothesis is that we hope that the shared representation will capture an equivalence that if for the number of heads to predict should be 0. If it should be 0, then the scores for the arcs will be low, and vice versa. But obviously, in multitask learning, the impact of the auxiliary tasks is very indirect. So maybe I'm going to skip. How much time do I have? 3 minutes, yeah. So this is the gory details of the how you compute the scores of the arcs and the scores of the labels, and how you represent, you perform the prediction of the auxiliary tasks. And I'm going to switch directly to the results. Sorry for this big table. So these are results on French syntactic graphs. So the bad news is that no single auxiliary task allows to improve results. But there are some combinations that do in a statistically significant way. So in particular, this combination, so H is predicting the number of heads, and B is a way to predict the set of labels of incoming arcs. So this is on French, and on English, we do have some modest improvements. So there are small improvements, but the good news is that it's systematic over all the data sets that we tested. So for the 3 kinds of annotation schemes for English, and also for the in-domain test set and the out-of-domain test set. So it's modest, but it's systematic. Yet it's not, it doesn't provide state-of-the-art results. So the sequential model that I mentioned before is better, and currently the state-of-the-art is obtained by automatically finding the right combination of several pre-trained language models. So it's very far from what I'm presenting today. So here is my conclusion. So we have modest but systematic gains. It's a simple technique, and it's orthogonal to the actual parsing algorithm or neural architecture. So actually it could be used for any kind of neural parser. And I thank you for your attention.